Everyone. Ooh, that works. So thanks for all for coming. This is building your own web analytics service. So we're going to go, it's a 200 level track, so we're not going to go too deep into anything, but we're going to sort of cover a whole bunch of technologies we use that have allowed us to build this out, and there should be lots of room for questions at the end, so let's get started. So first of all, who am I? So my name is Jonathan-Keebler. I'm at Keebler on Twitter. I've worked with a lot of media companies over the years, and the latest one was CTV. It was the largest media company in Canada, and we built a lot of video players for their news sites. And so scale and availability and things like that were always sort of at the forefront. So after that, I went on in 2008 to found Scribble Live with my co-founder, Michael DeMonte. And Scribble Live, we bootstrapped from the ground up. We were using our own credit cards and things. So we had to find ways to do things cheap, but yet work with really large media companies. So what is Scribble Live? So Scribble Live is the leading provider of real-time engagement management solutions. So we enable real-time publication and syndication of digital content for customers all over the world. So usually that takes the form of live blogs and interactive real-time experiences that they use to cover news in real time or engage with an audience, Q&As, all sorts of stuff. We work with a lot of brands too. And so just to give you an idea of some of our customers, CNN is a really big customer. You guys probably know down here quite a bit. ESPN. We work with customers in 14 different languages all around the world to power these sort of experiences. So obviously, scale is huge for us because if something big happens in the world, it's not just one of our customers covering it, it's probably all of them that are interested, or a big subset of that. So Amazon has been a great product for us, and they've asked us today to talk about a pattern that's worked really well and allowed us to build out this analytics platform we use. So that's what we're going to do. Today we're going to build your very own analytics service. It sounds a little crazy, but I swear you can do it. We're going to use some really cool buzzwords. So we're going to use node.js on Amazon EC2 for our web servers. We're going to use DynamoDB as the database. And we're going to use Hadoop running on Elastic MapReduce to do the roll-ups of data. So to sort of extract more information out of the data we're collecting. So why would we do this? Why would we go and build this stuff? So Scribble Live tracks what we call engagement minutes across our customer sites. And what an engagement minute is 1 minute of a user watching a web page. So it's how many eyeballs you have on your events. So for us, for our customers, understanding how many people are watching their events, if what they're doing is successful, is a really key thing for them to understand. And so to give you a sense of scale, we do about 2.5 billion of these a month. We've seen 120 million in an hour, so it's very spiky because it's driven by how interesting the news is. What people, if people are asleep, if news is a story that's continuing over days and days, it's something that's been really important for us to track. And what we found was the big analytics providers couldn't do it. They either didn't have the features to do it in real time the way we needed, or they were too inaccurate. Not to name any names, but some of them were underreporting by as much as 30%. Because they just don't see users the same way we do. We see people, they might be sitting on that page for half an hour watching something. So looking at just page views and things like that isn't very helpful. So what we're going to do is we're going to go through what we've done here. It's a very basic stack at a high level. The visitor traffic comes in, they're hitting an our Elastic load balancing, and then they're being distributed to a whole bunch of node.js servers. And then those node.js servers are writing back to DynamoDB, and then DynamoDB is having its data extracted, cooked by Hadoop, and put back into Dynamo. So we're going to go through every step of this and see what we did. And a big part of this too is just showing you a pattern and some products that have worked really well for us. Even if you're not building an analytics platform, hopefully you can take away from this session some of the practices that we found have been really successful. So let's start by looking at the data structure in DynamoDB. So for us, we have tables broken out by minute, hour, day, and month. And the minute data is the stuff that's being written to live. So those Node.js servers that are in our stack there, they're all continually writing back that minute-by-minute data into Dynamo. And Dynamo has been a great product for that. The structure in Dynamo, anyone who's familiar with it, who uses DynamoDB here today? So yeah, pretty big number. I'd say about a third of you. It has two big concepts. First is a hash. So this is sort of an ID for your data. And so for us, this is a page ID. It can be anything. It could be a URL for this example. It doesn't matter. And the other thing we do is we use a range that is the time. So with DynamoDB, you can use these ranges to extract data for a certain time period. So we're storing the minutes in there, or the hours, or the days. And then the other thing, inside each of these items that we're storing in Dynamo, we're just storing a counter, the number of hits. I'm sort of simplifying this a bit, but you could store anything in there. You could have hits or unique hits or a whole bunch of data. The great thing about Dynamo is it's whatever JSON you want, essentially, you can jam in there. So looking at our Elastic load balancing, this is, we use a custom AMI, Amazon Machine Image, on EC2. So what it does is when we spin up the EC2, we've used Linux startup scripts to download the source for our application from Subversion and then launch it with node.js. So for us, doing a rollout is as easy as doing a rolling reboot of these servers, or turning on totally new servers and then sliding them into production. We use one load balancer in multiple zones. So we have those Node.js servers sitting in lots of different zones. And we use cookies on that load balancer to keep, per user, to keep people sort of in the same zone for deduplicating the data. We also use auto-scaling on the ELBs, which is, we've really just gotten into it recently. It's a great feature. We have these rules that basically if the CPU goes above 50% on our Node.js servers, or the network in is sort of around the 50 million bytes per minute mark, that triggers new servers coming online. So we can be assured that, say it's the middle of the night, there's a big breaking news story somewhere, our Node.js servers are going to scale up to handle that, however big they need to get. So what are the Node.js servers doing? Basically, they're accepting a request that has an ID of the item and a unique user ID. And we're doing this at the JavaScript layer. So you can imagine there's code in the browser that's running an AJAX call that's saying, OK, I'm user Jonathan. I just saw page 1, 2, 3, 4, and it sends that back to our servers. On the other side, what we keep is a dictionary that's based on the minute and the ID combination. So you can see in my example here, in that array, we've got a particular time, so January 1st, 2014 at 1:23 a.m., and we're saying that we got one more hit to item ABCD. So it's just a way for us to start aggregating the data down at the Node.js level. So we're not saying we have to write every single request back to Dynamo. We're sort of aggregating it within the minute, within the node, to help make data processing easier later on. We also have an array of what users have already been counted for that minute. So if the same user makes a request twice or something weird, they reload the page or something like that, we're deduplicating data by saying, we've already seen that person, don't count them again. And then at the end of that minute, we're writing the data back to Dynamo. So the whole minute goes on, we're sort of counting it in Node.js, and at the end of that minute, boom, we write it back to Dynamo. So one of the best practices we found really quickly was you don't want to write your data back in a loop. Like if you have a loop that says, I've reached this minute, I'm going to just write everything back as fast as I can, what happens is the throughput in Dynamo spikes really, really high for a few seconds because it's so good at taking all those requests, and then nothing happens for the rest of the minute. So you can even look at your throughput graphs in DynamoDB, and you can't even tell what's going on because you seem to be getting a lot of errors writing data, but looking at your graphs, it looks like it's well below whatever throughput limit you set. So at the end of the day, you have to keep increasing that throughput limit up and up and up, and which costs you more and more money, and you don't know why it's going on. So what we figured out is you really have to stagger your writes to Dynamo over a minute. So we look at how many writes have to happen. So say, really easy example, we have to do 60 writes within that minute. So we do the math, and we say, OK, that's about one write per second, sorry. And we just write at that rate. And so it keeps our throughput to Dynamo really nice and level. We can see it in our graphs. And we've actually saved thousands of dollars a month just doing that practice. It really makes it that much more efficient. So here's what our calls to DynamoDB look like. So it has an update function. And we're just saying add X to the minute ID combination. So if I'm one of the node.js servers and I've just completed my minute for page 1234, I'm just going to write back to Dynamo and say, add 10 to that hit counter that you're running. So because Dynamo has atomic addition, you can really have an unlimited number of these Node.js servers writing back at exactly the same time, and you're going to get the correct number at the end of it. You're not going to lose counts because there's concurrency happening. So that atomic write has been a great feature of Dynamo we love using. So then we've got this table of minute-by-minute data. So you can imagine for event 1, 2, 3, 4, we've got every single minute, how many people were looking at it. The next step is to go from the minute to our hourly data. So we do that by rounding down to the nearest hour. Here's the equation we use, and summing the number of hits for each minute of that hour. And I'll show you how to do that in a sec. Something we do to really make this run a lot faster is we only look at the last 24 hours. So this is a judgment call we made. It takes about 6 hours to run through our data. So we only look at the last day to sort of save some time. And we do the exact same thing to go from hourly to daily and daily to monthly. So it's always, round all the data down to the closest hour, sum it all up, put it back into Dynamo. So on Hadoop, we're using Hive scripts to do that. And here's an example of what we're doing. You can see at the bottom there where we're doing the group by item, so the item ID, as well as the rounding operation. And then in the select, you can see we're summing that up. So anybody who's looked at SQL query language or something, Hive is very much the same syntax. It's really easy to get going with, which is, at the end of the day, why we started using it. It's very straightforward, and you don't have to get into Java or anything like that. So to set up our Elastic MapReduce, anybody who's played around with it a bit has probably seen this screen. So we create a new job flow by saying, run your own application, and we choose Hive programs. So we're saying, set up a Hive Hadoop cluster for us. And Amazon makes this, we use console for all this stuff. It's so straightforward. You just click the buttons, and you're in a little while. It takes about 15 minutes to spin up. When you're setting it up, we choose an interactive Hive session. Anyone who's familiar with EMR, there's a couple ways you can use it. Some people really want to just have it execute a job and then be done. So there's startup scripts and ways that you can get Elastic MapReduce running your job right from the get-go, and you don't have to deal with anything. For us, we want this job continually running 24 hours a day, 7 days a week, forever. So the way we approached it is we wrote a cron job that cycles every 15 minutes to check if the Hive job is complete. So if it is complete, so if it's done doing its work, it downloads the newest Hive script and then runs it again. So that way, say we find a way to optimize the script that's running, or we want it to do a couple more things. We want to go from monthly to yearly, for example. It's as simple as putting our new script into our deployment bucket and waiting for the last job to run, and then the new jobs will kick in. So for us, it's been a great way to run Hive. The advantage of running an interactive session like this, too, is that you can log into the machines at any time and see how your jobs are progressing, run your own jobs if you think you might have a new way to sum up this data even faster. It's been a great tool for us. And then we're using Amazon CloudWatch to see if the jobs are taking too long. So, sometimes these jobs can, start taking hours, more than hours, days. And so CloudWatch lets us track if, the throughput level is a problem, or if there's, the job hasn't run for a few hours, something's crashed it. And so CloudWatch is how we really keep track of that these things are healthy, that they're running properly, and that, our data is getting crunched. So here's an example of one of these cron jobs. Anyone who's familiar with Bash should find it pretty straightforward. We're really just looking at Hadoop's job list and seeing, is there a job running right now? And if there isn't, then at the last line there, we're downloading the new rollup script and then starting it executing. For us, it's been a great pattern to store our scripts, especially when we're talking about our Linux instances, to store our scripts out on S3 and have this sort of pattern where machines turn on, they download your script from S3, and then spin it up. A lot of people do another method where, with an Amazon machine image, they actually bake the script into the image, and it turns on with the right script already on. That works really well, too. But for us, we really don't want to be in the practice of turning machines on and off constantly. It's easier for us to just reboot them. So then, looking at our application API. So at this point, the language really doesn't matter. For us, we're a .NET shop, which most people find pretty funny because we're a startup. But to get the data out of Dynamo, it's as simple as using their query command with the hash ID, which we talked about before. That's sort of this is page ID 1234 or the URL or whatever you're tracking on, and then a range. So we were able to say, give me all the data between 4 p.m. and 5 p.m. Return it all to me, and then I'm going to cook it on the application side. One thing we found is that because we're running these MapReduce jobs, they can take a while to run, and for our customers, they need the data immediately. It's not good enough to say, wait a day, you'll have your analytics on your event. We need to know right now. So what we do is we actually, say someone asked for 2 days worth of data. So we know that we're going to have the data from yesterday already cooked, but we don't know about today. That job hasn't completed yet. So what we do is we actually say, give me the hourly data from yesterday, and then for today, give me all the minute-by-minute data. So you can imagine this gets really easy if it's the beginning of the day. At the end of the day, it's a bit more data. But at the end of the day, you end up with a manageable number of data points in your application code. And then with those data points, we sort of do the same things that we do with the MapReduce. We roll up that data in the application itself. So what we're able to do is produce API results to our customers that have the latest minute up to the latest minute, and they're able to get that 24/7 a day without waiting for the MapReduce job to finish up. So here's some graphs. Everyone loves graphs. This is what our performance looks like from network in. So this was a couple weeks ago, and what we found is you can see about midway through, something started happening. There was a big news event happening. So you can see our traffic just growing bit by bit, with the servers that were already online. And at some point, they hit that magic threshold where it's time to turn on more servers. And that's really where auto-scale kicks in. So you can see we've got it set to turn on new servers, 2 new servers. So it's really easy to say, turn on 2 more servers, or maybe you've got traffic that's scales so quickly you need to turn on 10 more at a time. But in this case, you can see those 2 new servers, a green one and a blue one, come up to help their brothers deal with this traffic. Looking at the same time period on the CPU utilization, you can see what was happening. The CPUs were getting higher and higher and higher on the existing nodes, and at some point, node would have just crapped out, and we would have started losing these analytics. So you can see the 2 servers came online at about 12:45. You can see it takes about 5 minutes for them to really come online and to download the scripts and get going. But then immediately after they get into the Elastic Load Balancer, they start receiving that traffic and really helping all of their brothers deal with this traffic spike. So we've been using this for about 8 months now. It's something, we started using DynamoDB really as for an MVP. We like to stay agile, do a lot of continuous integration, that sort of stuff. And Dynamo came out right as we were starting this product, and we were sort of like, why don't we try it? It's a key value store. We don't have to deal with setting up Cassandra or something else like that. And it was amazing how quickly it made it into our production environment. Because the moment we started thinking about production and doing production traffic tests, it was really just a matter of increasing our throughput on DynamoDB. And it scales that easily. So, the amount of hours that it saved for us over those months of, hours we would have spent configuring key value shares or learning Cassandra, and then having to scale that up so that we could use it in production have really been significant. And like I said, too, some of the tricks that we've learned along the way, such as how limiting the throughput, limiting your own rate of throughput to Dynamo, have allowed us to go from spends of tens of thousands of dollars a month down to the single thousands, and in some cases per table actually down into the hundreds. So there's a lot that you can get to know about Dynamo that will allow you to save money. And for us, our Amazon team has really been a great resource for that as well. Any of you that aren't under the NDA with Amazon right now, it's worth reaching out to your account manager, because what they can actually do is get you in touch with the people that can actually tell you a bit more about how Dynamo works behind the scenes and sort of give you tricks to really scale your use of Dynamo down, because you understand a bit more of how it works. So it's been a great partnership for us, and I blew through those slides really, really quick, so we have lots of time for questions. Does anyone have any questions about what we've done? Yeah?
Based on the traffic you get, go up or down, and then you said you had an interactive high position. How do you control the number of slaves or workers?
Well, so the question is, we've got traffic that scales up and down really quick. How do we decide how many workers to have in our Elastic MapReduce? Well, for us, traffic is really targeted traffic. So if there's a really big story, you can imagine that's a lot of people that are interested in that story, but it's not a lot of different stories that are going to be hit at the same time. Like you can imagine the traffic to one story might go up by 1,000, 10,000%, but the number of stories being written, like different stories by different customers, might only go up by 100, 200%. So we actually don't need to turn on any more workers, because the aggregation is all being done at the node.js level. So those node.js servers, whether they count 1 hit per minute on an event or whether they count 100 hits per minute on an event, the same amount of writing to Dynamo is happening, and as such, the same amount of cooking by Amazon MapReduce happens. So we really don't have to scale them up dynamically. If we did have the problem you were talking about, the way we'd probably approach it would just be to spin up new Elastic MapReduce instances every time. Yeah?
Because you're rolling out from minutes to hours and days, how do you keep track of uniques on the higher time frame?
Well, we've obfuscated some of this. So the question is, if we're rolling up the data to hours and days and months and everything, how do we keep track of uniques? For us, we actually use the same pattern for uniques as we use for hits in this example. We end up counting the number of uniques per node server. So if we get a total count of uniques, but we don't actually understand who the uniques are. And then we write that piece of data right back into the node DynamoDB the same time we do the hits. So if you think about what our item looks like at Dynamo, there's a whole bunch of different values in there. The first is just how many eyeballs do I have? A second would be how many unique eyeballs do you have? We actually go as far as having how many page views and all these other things as well. So there's really, we've sort of simplified it here, but there really is no limit to the amount of data that you can store in a Dynamo item up to the, I think there's a 1 meg cap on there. Yeah? Yeah, so great question. So the question is, in our example, we're just sort of worrying about totals. We don't really care about where they're coming from or anything like that. That's actually a problem we solved in the last few months after we wrote these slides. And we really use the same pattern. So in this example, the ID, the item ID that we were sending back to Dynamo was just an event ID for us. So we know it's this event going on. The pattern we used was basically to do the same thing per refer. So for event 1, 2, 3, 4, this is the amount of traffic that's coming from Google, or this is the amount of traffic that's coming from Yahoo. And we wrote that back to Dynamo on a minute-by-minute basis the exact same way. So what the end result is that you end up with a MapReduce that is much, much bigger because you've got all this data. And definitely ran into challenges with customers that would put us, for example, on every page of their site. That's just a huge amount of data that you have to crunch through. But of course, with Elastic MapReduce, the solution to most of that is, instead of 3 workers, we're just going to put in 20, and it just works. So we use very much the same pattern for that. Yeah.
I didn't quite understand the part that you put in the Elastic MapReduce and how do you extract data to DynamoDB?
So Elastic, if you use Elastic MapReduce, and in particular if you use Hadoop and Hive right in there, they've got a connection to Dynamo already. It's actually baked into the Hadoop solution. So if you look at the Hive script that we were using, you're able to, right there, you're able to code against Dynamo as if it were a SQL table. So you can see here this is exactly like SQL query language, but this metrics hourly table that we're talking about is actually a DynamoDB table. So the same way the select is able to pull information out of Dynamo, you can do an insert back into Dynamo. So in this case, we're doing a bulk insert, the equivalent of a bulk insert for SQL, but you could do it on a case-by-case basis as well. You could do cook data up somehow and then do insert operations. It really is the same sort of syntax to connect to Dynamo. And you get that, and for us, that was one of the main benefits to using Elastic MapReduce versus our own Hadoop installation, that you get all that for free. You don't even have to think about it. I think there was examples in their white papers on how to use Hive with DynamoDB, and it's really that straightforward. Yeah, quite.
You said that you're storing the data temporarily inside of each node, and then staggering it right at the Dynamo,
Yeah.
which introduces a sort of statefulness to each of those EC2 instances. And if you lost one, you potentially lose data. Has that been an issue for you?
So the question is, we're waiting until the end of the minute to grab to add up the data on the node.js instances. What happens if we lose one, basically, by surprise? This has been a big problem for us with autoscale, actually. Because autoscale, what we found is that it kills those servers really, really quick. And we've played around with runtime levels and things like that to try to get that data off before the machine shuts down. But really, we haven't found a way to do that. If anyone is, yeah.
Well, have you considered staggering that process so that the nodes write to a queue like SQS and have a separate set of processes which can reliably pull off of it and push it into Dynamo?
Yeah, I think that would be a good pattern. So the question, his comment is, what if we used a queue or something? For us, you'd still have to write it to the queue. So for us, writing into Dynamo or writing it to the queue, it was about the same amount of latency, which is why we were like, let's just write it to Dynamo directly. You would have to get to a pattern like that, though, if you actually cared about who the people were. If you wanted to record every single unique hit and get that put somewhere, you definitely have to do it that way. For us, we're sort of more talking about big numbers of people, big timelines. For us, getting the data quickly is way more important than being able to do analysis at that level on it. And so that's a trade-off that we had to make. Yeah?
So for the same-day rollups, do you have to do a lot of range querying? And if so, then aren't they time-consuming?
Sorry, are they what?
Aren't they time-consuming range queries if you want to get rollups on the same day?
Yeah, so the question is, are our range queries for the rollups time-consuming? When we're talking about data for a day, it's still only 24 hours times 60 minutes. It's not a large amount of data. And also, we're talking about mostly numbers. So we can grab this data back really efficiently from Dynamo. The query command actually they have a great option where you can return only certain information in the result. So, for example, we can return, say we're only interested in that engagement minute number. I told you we actually have engagement minutes and page views and everything else, but say we only care about that engagement minute. We can say, Dynamo, only return me the data points in this range and only return me the time and the engagement minute value for that time. So you end up, you're talking about, 3,600 ints. Like it's not a really big return result. And so we're able to get that back in a very timely manner. Like I think it's well less than a second to get all that data out of Dynamo.
I'm thinking that you have a lot of columns, right? For each column per user ID. You've got like really wide rows.
No, we actually store, the items in Dynamo are actually the item ID combined with the time. So for one item, it doesn't have all the different times in it. There's actually a data point for the item time combination. So there's say we're page X. We have page X at 1 o'clock, then we have page X at 1:01, then we have page X at 1:02. And so the data, you can grow it as quickly as you need. And also, more importantly, you can do those atomic adds very efficiently on all those data points. And something else that we didn't touch on was, say, Node.js servers, all those Node.js servers running out there, they'll never have clocks that are synced up 100%. So, having the data like that, your last minute of data is going to be continually written to over the course of, maybe a couple minutes, just based on how the clocks are ticking in each of those Node.js servers. But when it all averages out, it ends up being a really smooth data graph that we're able to extract from it. Yeah? Sure. So the question is, on each Node.js server, where are we saving those results temporarily? So for us, the beauty of Node.js is that it can really take a beating. Like if our traffic is scaling really suddenly, it can just take that pounding. And so with what we do is we actually store it in memory. So we're using the array construct in Node.js. In JavaScript, same thing. I think it is technically an array, but you can sort of use it like a dictionary. And so we just use those to hold the data. We're using M1 medium instances, so there's plenty of memory to store a minute, maybe 2 minutes of data in memory. If we ever hit a memory constraint, we'd probably just upgrade to the M1 larges and increase our limit quite a bit. Yeah, so sorry, what's the question? It's just a ticking of the clock. So if we're starting at 1 o'clock, from 1 o'clock until 1:01, every single request comes in, gets sort of routed into one of those arrays. And then there's an asynchronous process on Node.js that's ticking every minute. And when it reaches that minute marker, it says it's 1:01, that's when it starts the process of writing the data back. But because at that point, it actually knows I have to do this many writes, I have to do 60 writes, I have 60 seconds before the next time I have to do this, so I'm going to do 1 a second. And then that's a loop that we're sort of putting a timeout in, essentially. Yeah? Sorry? That's true. So if node goes down, so the question is, what if node goes down? So if node goes down, we're going to lose whatever the minute we're in, right? Because it won't be taken out immediately because the elastic load balancers, we run a health check that checks, I think it checks every 10 seconds, and if it fails 3 of those, it's out. So there is a possibility that we might lose a minute of data. The way we deal with that is by having more instances. So we could probably run everything we do on 2 of the largest instance types, and put one in each availability zone, and away we go. But if one of those went down, we'd have 50% of our traffic, first of all, that would smack the other instance, which would be a problem. They probably couldn't deal with that. And we lose 50% of the data. So instead, our strategy is to use really small instances and have a whole bunch of them. So if we have 10 instances and one of those goes down for some reason, we're only losing 9/10 of the data, and that 1/10 of the load gets spread across 9 other machines. So it's a much more efficient way for us to operate. The same rule applies for availability zones. If we have 2 availability zones and one whole zone goes out, which is pretty rare these days, that would mean all that traffic would have to reroute to one availability zone. That could be a problem. Instead, it's a better strategy to use as many availability zones as you can. And at that point, it's really just a cost-benefit analysis. How many instances can you afford to have online to deal with your traffic? Yeah.
In your Hive script, how are you deciding which hour you're actually calculating, or like what's triggering like the next hour to calculate?
Yeah.
What piece of it is dynamic?
So the question is, for a Hive script, how are we deciding, how we look at the next hour? So if you look at the where clause here, we've got where our time is greater than that formula there. What it's doing is actually saying go back to midnight on whatever day you are, then go back 24 hours behind that point. And so, what that means is that you're covering at least a 24-hour block. At worst case scenario, you're going to be covering a 47-hour, 59-minute block. Then the same way as in SQL, this is going to do a roll-up on an hourly by hourly basis. So if you look by the group by clause there, we're actually rounding down to the hour. So each data point that Hive encounters, it's going to roll down to its own hour, and that's where the MapReduce is happening. So the mapping is it taking all that data and going down to the hour, and then the reducing is, the mapping is getting the hour per item, and then the reducing is summing up those hours for each of the items. So this algorithm is actually saying, say you're running it at 4 o'clock in the morning, it's actually coming up with a new total for 1 a.m., for 2 a.m., for 3 a.m., and for 4 a.m. as far as you've gone along so far. So that way, we don't have to generate these dynamically. Another pattern would be, though, to actually generate this dynamically, write it somewhere using a cron job or something, and then run it in Hive. That would be another strategy, probably. Yeah? Sorry, the amount of... Sure. So our Dynamo, the question is how big are our DynamoDB tables? We have some tables that have billions of points of data in them, terabytes of data. Our throughputs, I'm looking at Mike because he actually built this. What are our throughputs? A couple hundred right now? 100, 200. Yeah, 100 to 200. So, and really, we were in the thousands. We were in the tens of thousands of throughput. We got it to come down to the hundreds by employing the strategies that we used here, as well as if you start getting huge amounts of data, what happens is the MapReduce jobs start taking a long time. So one pattern that, this is a bonus pattern for everyone who stuck around. One pattern that we used was to actually put the minute-by-minute data into month blocks. So we would have the minute data for November, and then the minute data for October. So that really makes the MapReduce jobs run a lot faster as well. And so that's how we dealt with it. Essentially, what we found, though, is the amount of data that you're writing to Dynamo doesn't really affect anything. It doesn't really matter how much data you're putting in there, but you have to make sure you're writing it evenly and that you're extracting it evenly. Like if there's one record that you're really, really pounding, like everybody's going to that one record and you're hitting it tens of thousands of times a second, that's when the throughput of Dynamo is going to start to be a problem. Yeah?
When you add the aggregation to the back end of DynamoDB for the reporting purposes, right? DynamoDB is a good candidate for the reporting purposes?
Yeah, so the question is, when we write it back, do we do it for reporting purposes? So yeah, that's exactly it. If our users are looking at a day's worth of data, it would take a long time for us to graph all the minute-by-minute data for that entire day, and the graph would be really like jittery. So by having it stored in those blocks, we're able to make nice graphs very, very quickly, because it's really just as easy as pulling the information out of Dynamo. So if I want to give you an hourly graph for the past 24 hours, that's actually only 4 data points that I have to get out of Dynamo. So Dynamo will do that in milliseconds, and then you can draw the graph in however long it takes the browser to draw it. So it really saves us a lot of time on the rendering side, on the visualization side, as well as the storage in Dynamo. There's just not much data that we have to put in and out. The MapReduce is really doing the bulk of the data crunching and understanding what that data is. And then we're just using the cooked up version of that. Any other questions? Yeah, one in the back. So the question is, tying into Dynamo through a Hive script like this, what throughput does that affect? Is that a different throughput, or is that the throughput on your table? The simple answer is it's the same throughput. When you set up Hive, I think by default it will use half your throughput that you've made available. So if you made 100 available, Hive will automatically use up to 50% of that, at which point it will start throttling itself. So that is something that you have to think about. It's especially important when you're looking at extracting large amounts of that minute-by-minute data to do the MapReduce. If you're doing that, that could actually be a huge amount of your throughput that you're spending just doing the MapReduce job. So one way is to let your jobs take a little longer by reducing the amount of throughput that your MapReduce, that your Hive jobs can run. Another way to do it is to just do it in off-peak times. So if for us, we're really pounding DynamoDB, there's a lot of requests coming in, that might not be the best time to start a huge MapReduce job. Whereas if we wait to the middle of the night, wherever the country is that's doing that traffic, we might have almost 99% of that throughput left unused. So there's some ways to get around it, but I think it's going to depend on an implementation basis.
How do you deal with geographical redundancy?
So how do I deal with geography?
With geographical redundancy, I mean, you say you have an Elastic Load Balancing node.js candidate.
Yeah.
After you have an analytics endpoint available in multiple physical regions.
So the question is, how do we deal with geographic availability for something like this?
Yeah, let's say, for example, US East and all of US East will be rocket failure, whatever is not accessible.
Yeah, so how do we deal with just having all our servers in US East? So it's true, right now we run out of one region, multiple availability zones. DynamoDB is tied to one availability zone. So I think this is where, if you wanted to crack that nut, you'd have to get into the pattern that the gentleman beside you was sort of talking about, where you're using a queue to process that information, you're storing it somewhere else. The way I'd probably look at it would be to write it twice into two different regions, and actually get full duplicates of the data. But that's, for us, like I said, having this data, it's important to us, but we're not a bank. It's okay if it's not 100% accurate. We're happy with 99.99. So we're only working in one region right now. All right, well, thank you so much for attending. Thanks for the questions. And if you have any other questions, I'll be roaming the halls. I'll probably be up here for a while. So come on up and say hi. So thank you very much, everyone.